Statistical Process Control, or SPC, is a methodology used to monitor and manage manufacturing processes by analyzing data variation. It is used to ensure processes remain stable and capable of producing consistent quality. The benefits include early detection of process shifts, reduced waste, and improved reliability. However, liabilities exist. It requires disciplined data collection, a strong understanding of statistical theory, and can be misinterpreted if operators are not properly trained. Moving to our first set of tools. For subgroups of 10 or fewer, we use X-bar and R-charts. The X-bar chart tracks the process average, while the R-chart, or range chart, monitors within subgroup variability. The equations for the upper and lower control limits use constants like A2, D2, and D4. These constants are derived from the distribution of sample ranges relative to the population's standard deviation, originally developed through statistical simulations to provide a reliable 3 sigma estimate. Looking at the graphs at the bottom, we plot the subgroup averages and ranges sequentially to see the process's inherent stability over time. When subgroup sizes grow larger than 10, the range becomes less efficient. In these cases, we use X-bar and S-charts. Here, S represents the sample's standard deviation, providing a more precise estimate of variability. The constants used here, like C-4, B3, and B4, are mathematically derived to unbias the sample standard deviation, ensuring our limits remain accurate as sample density increases. The graphs below reflect this by showing the standard deviation of each subgroup, rather than just the range. Beyond simple limits, we use out-of-control rules to identify non-random patterns. Rule 1 flags any single point beyond 3 sigma, signaling a major shift. Rule 2 flags 9 points in a row on one side of the mean, indicating a bias. Rule 3 detects 6 points trending upward or downward, suggesting gradual drift. Rule 4 flags 14 points alternating, which often reveals cyclical effects. Continuing with more subtle tests, Rule 5 flags 2 out of 3 points beyond 2 sigma as an early warning. Rule 6 identifies 4 out of 5 points beyond 1 sigma. Rule 7 shows 15 points in a row within 1 sigma. This is actually suspicious, as it implies a lack of natural variation. Rule 8 highlights 8 consecutive points outside the 1 sigma zone on both sides, suggesting a mixture of 2 different processes. Finally, let's examine a process failure analysis. In this scenario, data is collected over 8 hours. We calculate the mean and range for each hour and plot them. The process remains stable until time 6. At this point, the mean jumps to 108.4, which is clearly above our upper control limit. The process has failed because it violated Rule 1. This indicates an assignable cause, such as a tool break or material change, that has pushed the process average beyond the bounds of natural statistical variation.